Every single time your spark plug fires, a portion of the fuel you just paid for never actually burns. It doesn't contribute to combustion, it doesn't generate power, and it certainly doesn't move your car forward. Instead, it remains in larger, inefficient droplets that fail to fully atomize, slipping past the combustion process and exiting through your exhaust valve as unburned hydrocarbons. In simple terms, you are quite literally watching your money vaporize and disappear out of your tailpipe with every drive. This is not a rare occurrence or a mechanical defect specific to one engine. It is a fundamental inefficiency present in all internal combustion systems. And this exact inefficiency is what fuels an entire global industry. The fuel additive market, valued at roughly $8.4 billion annually, is built around selling solutions to this very problem. Walk into any auto store or gas station and you'll find brightly packaged bottles placed strategically at eye level, priced anywhere from $12 to $22 for a single treatment, marketed as premium fuel conditioners or performance boosters. But what most people never realize is that the actual chemical cost required to improve fuel behavior inside your engine is only a fraction of that price, often between 50 to 70 cents per tank. The enormous gap between that true cost and the retail price is not accidental. It exists because the industry relies heavily on branding, packaging, and positioning to keep the real solution out of sight. At the center of this discussion is a simple, widely available compound, acetone, with the chemical formula C3H6O. Known commonly as a strong solvent used in cleaning and industrial applications, acetone has properties that can influence how liquid fuel behaves at a molecular level, particularly in terms of surface tension and evaporation characteristics, when mixed in extremely controlled amounts with gasoline. The theory behind its use is tied to improving fuel atomization, the process by which fuel is broken into fine droplets before ignition, which plays a critical role in achieving more complete combustion inside the engine. To understand why fuel efficiency is lost in the first place, you need to understand one critical concept: atomization. When gasoline enters your engine, it isn't supposed to flow as a liquid stream. It is sprayed as a fine mist of microscopic droplets. The reason this matters is simple physics. The smaller each droplet is, the more surface area it exposes to oxygen in the air. More surface area means a faster, more complete combustion when the spark plug ignites the mixture. But here's where modern fuel introduces a hidden inefficiency. Today's ethanol-blended gasoline has a surface tension profile that resists breaking apart into ultrafine particles under real engine conditions. Instead of forming a perfectly even mist, a portion of the fuel remains in larger, heavier droplets. These droplets do not fully combust before the piston reaches top dead center, meaning part of the fuel charge never contributes to power and is instead expelled as unburned hydrocarbons through the exhaust. That's wasted energy, wasted fuel, and ultimately wasted money. Now this is where the chemistry becomes interesting. Acetone, a simple compound with the formula C3H6O, has a distinct surface tension characteristic that allows it to interact with gasoline at a molecular level. When introduced in controlled, minimal quantities, it alters the overall surface tension behavior of the fuel mixture. The result is a change in how fuel droplets form and break apart during injection. Instead of remaining as larger droplets, the fuel can form a finer mist, increasing the total surface area available for combustion. In theory, this supports a more complete burn inside the cylinder. There's also a secondary thermal effect often discussed. Acetone has a relatively high rate of evaporation, meaning it can absorb heat as it transitions from liquid to vapor. This process can slightly cool the incoming air-fuel mixture, increasing air density inside the combustion chamber. Denser air contains more oxygen molecules per unit volume, which can contribute to more efficient combustion under the right conditions, without requiring any mechanical modification to the engine. However, it's important to separate controlled laboratory findings from real-world application. Some experimental studies have explored oxygenated additives and solvent-based blends, reporting improvements in combustion efficiency and reductions in certain emissions under specific test conditions. For example, controlled engine tests have shown measurable reductions in carbon monoxide and unburned hydrocarbons when fuel atomization improves. But these results are highly dependent on precise mixtures, controlled environments, and specific engine types. Translating that directly into everyday driving conditions is far more complex. Real engines vary in design, fuel injection systems, sensor feedback loops, and ECU adjustments, which means outcomes are not guaranteed to scale in a predictable way. While improved combustion efficiency can theoretically reduce fuel waste, claims of large percentage fuel savings in real-world driving should be approached cautiously, as they often depend on multiple variables beyond just fuel chemistry. Long before internet forums, viral videos, or even modern fuel research papers existed, this idea was already being explored quietly by people who depended on engines for survival, not theory. In post-war Japan, particularly in the mountainous regions of Hokkaido and Nagano, fleet mechanics maintaining heavy transport trucks faced a harsh reality. Freezing temperatures and high-altitude conditions made fuel behave unpredictably, leading to poor volatility, incomplete combustion, thick black exhaust smoke, and constantly fouled carburetor systems. These were not minor inconveniences. They were operational failures. Through trial, error, and necessity, mechanics began experimenting with small quantities of readily available solvents to stabilize combustion. Among these, acetone was one of several substances reportedly tested. In anecdotal accounts, passed down through mechanic circles, small additions appeared to improve cold starts and reduce visible smokes. However, these practices were never formalized in official manuals, and no standardized documentation exists to confirm consistent results across fleets. What survived instead was word-of-mouth knowledge, practical experimentation born out of extreme conditions rather than controlled science. A similar pattern appears when you look at early industrial and military experimentation in Europe. During the 1930s and 1940s, researchers and engineers across multiple countries were actively studying fuel behavior, especially in aviation and heavy industry, where efficiency and reliability were critical. Various oxygenated compounds, including alcohols and solvents, were tested to improve combustion characteristics in lower-grade fuels. While acetone has been mentioned in some historical discussions of experimental blends, most documented programs focused on more stable and controlled additives such as ethanol or methanol. In parallel, industrial operations like mining in Scandinavia, including regions such as Kiruna in Sweden, faced serious air quality challenges from diesel emissions in enclosed environments. Engineers explored multiple methods to reduce carbon monoxide and particulate output, including ventilation systems, fuel quality adjustments, and additive testing. While improvements in combustion efficiency were observed through different approaches, there is no widely verified historical record confirming standardized acetone blending at scale in these operations. What is clear, however, is that the problem of incomplete combustion and the search for solutions has existed across industries for nearly a century. In the United States during World War II, fuel efficiency and vehicle range were critical concerns, especially in remote theaters where supply lines were stretched thin. Military engineers conducted extensive testing on fuels, lubricants, and engine performance under varying conditions. Declassified records show numerous experiments aimed at maximizing efficiency and reliability, but these primarily involved adjustments in fuel composition, engine tuning, and logistics strategies, rather than reliance on single solvent additives. While small efficiency gains, often in the range of a few percentage points, were considered valuable, they were achieved through controlled engineering approaches, rather than simple field fixes. This distinction matters because it highlights the difference between structured, repeatable science and isolated experimentation. What ties all of these stories together is not a single hidden secret, but a consistent truth. Mechanics, engineers, and operators across the world have always searched for ways to improve combustion efficiency using the tools available to them. Sometimes those solutions came from formal research, and sometimes from hands-on experimentation. But only in modern times have we been able to fully study fuel behavior at the molecular level and understand the precise mechanisms behind atomization, evaporation, and combustion. The idea that fuel efficiency can be influenced by chemical properties is absolutely real, but separating verified science from anecdotal practice is what turns curiosity into true understanding. Before you even think about applying anything to your fuel system, you need to understand one critical point. Modern engines are extremely sensitive, and using the wrong chemical or incorrect concentration can do more harm than good. There's a lot of misinformation online about using solvents like acetone in fuel, but this is not a manufacturer-approved method and is not recommended by automakers, fuel companies, or engine engineers. Products like nail polish remover must absolutely be avoided, not because they are less effective, but because they contain water, fragrances, and additives that are completely unsuitable for fuel systems and can damage components over time. More importantly, even pure industrial-grade acetone is not designed or certified to be used as a fuel additive in gasoline or diesel engines. Modern fuels already contain carefully engineered additive packages that are balanced for combustion, lubrication, emissions control, and compatibility with seals, injectors, and sensors. Introducing an external solvent into that system can disrupt this balance in unpredictable ways. When it comes to real, proven solutions, the safest and most effective approach is to rely on fuel that already meets recognized standards such as top-tier gasoline, and if additional cleaning is needed, to use additives that are specifically designed, tested, and approved for automotive use. These products are formulated to work with your engine's fuel system without risking long-term damage. Any exact dosage advice you may see online for acetone or similar solvents is not based on standardized engineering guidelines and can vary widely depending on engine type, fuel system design, and driving conditions. Even small miscalculations can affect fuel lines, rubber seals, injector performance, and emission systems like catalytic converters. From a practical standpoint, the best way to improve fuel efficiency and reduce waste is through a combination of proper maintenance and driving behavior. Keeping your air filter clean, ensuring your spark plugs are in good condition, maintaining correct tire pressure, and using the right engine oil can all contribute to measurable improvements in efficiency without introducing unnecessary risk. Modern engine control units are already optimized to adjust fuel delivery, ignition timing, and air-fuel ratios dynamically, meaning most of the hidden efficiency people are searching for is already being managed by the vehicle itself. If you look at the financial side realistically, consistently buying overpriced, unverified quick-fix solutions can add up over time, which is why it's important to separate marketing claims from proven engineering practices. Spending money on proper maintenance will almost always deliver more reliable and consistent savings than experimental methods. That's how you actually stay ahead of both unnecessary costs and potential repairs. And if you're interested in uncovering real manufacturer-level features that can genuinely improve your car's performance and longevity without any risk, the next breakdown is going to surprise you. There are built-in functions in many modern vehicles, especially in Japanese models, that can significantly reduce battery drain while the car is parked. Yet most drivers never even hear about them during delivery. That's exactly what we're breaking down next.